With all major units of the Joint Task Force at their overseas bases, final phases of training began in earnest, with installations and modifications of equipment being simultaneously accomplished. Final coordination of the tremendous organization had begun. To simulate the Test Able bombing mission, a practice bombing range was constructed on Erik Island. A coral strip was cleared, approximating the top side dimensions of the primary target. 4 spotting towers were placed on the island for plotting the bomb drops by the transit method. These towers were manned by Los Alamos personnel. A radar detachment was established on Prayer Island, 1.5 miles east, for the purpose of tracking the bomb-carrying aircraft, communicating with the bombing commander, estimating bomb impacts, making weather reports, and obtaining high-altitude wind data. Training was intense, not only for the air crews practicing bomb drops over Erik Island, but for all other airmen, as they flew their assigned courses in the exact positions described by the air plan. Training was equally exacting for the many crews on ground stations and aboard ships, all essential cogs in the maneuvers. The Air Attack Unit carried out 23 missions in which practice bombs were dropped, and 6 dress rehearsals for a total of 29 major training operations in which simulated atomic bombs were dropped. The average circular error was 537 feet, a remarkable record. Practice bombing missions for Crossroads developed bombing techniques to a point that might not have been attained in several years of routine training. Bomb crews learned to make corrections for differences between winds at bombing altitude and those observed by the radar unit. At Bikini, it was noted that winds at lower altitudes were sometimes at right angles to winds at the prospective bombing altitude. Conventional methods for ballistic wind corrections did not permit compensation for such a cross-trail component. A method was found for estimating this deflection error and correcting for it. This proved one of the valuable results of the tests. Weather characteristics at Bikini resulted in a decision to move the orbit of the photoplanes into 12-mile slant range on Able Day, 3 miles closer than had originally been scheduled. Results bore out the wisdom of this decision. Photographs at the closer range showed better scale and improved definition. Because of the low elevation of Kwajalein, a ramp and a bomb loading pit were needed. Seabees erected a ramp capable of supporting a B-29. This led to the pit. When the bomber was in position over the pit, powerful hoisting equipment was used for loading. Air-sea rescue units were given elaborate training and coordinated with the operational flight plan. These seaplane groups operated a shuttle service between Ibai and Bikini and participated in reconnaissance. A second air-sea rescue unit was established at Kwajalein because of the possibility of takeoff accidents during the air activities there. Never before has a field experiment depended so much upon photography. No other event in history has been so extensively documented by means of the camera's eye. There were cameras everywhere, in the air, on the land, on the sea, and beneath the sea. Some in towers on the atoll were shielded by lead an inch thick. Others, such as these in the B-17 drones, were aimed by television as they dived into the atomic cloud. Virtually every type of camera available was used in one capacity or another. Relative importance was almost equally divided between still and motion pictures, each being used to complement the other in recording phenomena. While the photographic coverage of Crossroads constitutes a complete and detailed record of the operation and provides an invaluable historical document, the primary objective of the photographic units was to deliver film technically qualified to serve as a basis for scientific analysis. This called for precision and control in all phases of the operation, from maneuvering of aircraft to operation of photographic equipment. Photography provided the basic instrument for accurate measurements of movement as a function of time. This was required to analyze blast forces and other properties of the bursts. Cameras in fixed ground positions on the island offered relatively few problems in photographic control. In the air, camera platforms consisted of aircraft orbiting the target at fixed altitudes and given slant ranges, at ground speeds as high as 300 miles per hour. The exact position of each camera aircraft in space at time of detonation had to be recorded. The exact position of the bomber in space at the instant of bomb release, and the exact position of the target ships in relation to each other a few seconds before detonation had to be determined. These relative positions were determined by photogrammetric plotting and radar plotting, each using photography as a prime implement. An electronic control system was devised for starting cameras automatically. This employed a radio relay receiver in each photographic aircraft to pick up timing signals from the Cumberland Sound, and time delay relay controls to distribute the different starting impulses required by the various camera setups. For example, the relay control, operated by a signal at H-2 seconds, started a Fastex high-speed camera at -1.5 seconds, and also started an Eastman high-speed camera at -5/10 seconds. Remote control boxes started turret cameras and K-24 cameras. Sequence control equipment started 3 or 6 high-speed cameras in a sequence pattern. A time recorder was designed to provide an accurate time record of the operation of cameras. This consisted of a motion picture camera, which photographs 24 small indicator lights mounted on a panel around a precision clock. Ultra-high-speed motion picture cameras were operated at speeds as high as 2,000 frames per second. Some cameras had cylindrical lenses and moving strip films to record the intensity of the light from the explosions. Other cameras, moving great strips of film continuously, were called streak or blur cameras and interrupted light beam recorders. Moving drum spectrographic cameras were designed and built to get the wavelength distribution of light at all stages of the flash. 9 75-foot steel towers were erected on 3 islands of the atoll, Bikini, Nu, and Amen. These towers provided camera platforms on fixed axes and were equipped with electrical controls which could be triggered by gremlin timers. At other stations on Bikini and Nu were some extraordinary photographic devices. These included instruments that could separate events 1/10 of a millionth of a second apart. The rate of shock wave expansion was to be measured by long focus, high-speed cameras coupled with light beacons dispersed within the target array to determine the properties of the shock wave as a function of distance. The rate of development of the ball of fire and the unfolding of temperatures were to be recorded spectrographically. Light intensity was to be followed photometrically in 3 colors. The bomb burst was the nearest parallel to the atmosphere of a star that man could produce. Yet, these measuring instruments were within 5 miles of the radiating surface. Information of interest to astrophysicists would have evolved from these instruments. All this information was to be recorded within a few milliseconds, and there would be but one opportunity. It was a misfortune that this opportunity was lost through failure of the timing signals. The automatic control for triggering the equipment was rendered useless by a premature start, and the change to manual control was not made in time to record initial phases of the burst. 19 Army Air Force planes and 17 naval aircraft provided a camera umbrella for the tests unlike any the world had ever seen. 8 F-13s and 2 C-54s were modified for the job. Each F-13 carried 38 cameras, and each C-54 carried 32 cameras. The B-17 drones were also equipped with automatic cameras. Navy aircraft assigned to photographic work included F-6Fs, TBFs, and PBMs. Automatically triggered cameras were placed aboard many of the target vessels, and cameras aimed from observer ships augmented this battery. New optical instruments, glare-reducing icaroscopes, were used for the first time to photograph the early stages of the ball of fire. More than 1,500,000 feet of motion picture film were exposed during the operation, and the number of still pictures exceeded 1 million. Field laboratories were set up at the Army Air Base on Kwajalein and aboard the Sidor. Chief processing and assembly point was the Naval Photographic Center in Washington, where new techniques were used for filing of the material. Commercial laboratories were also used for processing color film. To record necessary data during the tests, a great many new instruments were designed and manufactured, while thousands of standard instruments were brought into play. The manifold effects of the detonations required instruments to measure pressures and impulses, electromagnetic propagations, radioactivity, nuclear radiation, optical radiation, strains and stresses, winds, temperatures, waves, and many other local and remote phenomena. Elaborate sets of instruments were necessary to record seismological and oceanographic information. Pressures and impulses in the air and water, orientation of vessels with respect to 0 point, shock wave velocities, and the amount, quality, and time variations of light were also among the data to be determined. Many of the instruments were complicated and highly classified. Some were known only as black boxes. Others were such simple objects as pipes, cans, and oil drums. Still others were ball crusher gauges, aluminum foil rupture gauges, wire strain gauges, and piezoelectric gauges. Readings from many instruments were broadcast by radio and immediately telemetered. Some of the unusual measurements included changes in terrestrial magnetism, atmospheric pressure and conductivity, and ionospheric reflectivity. For remote measurements, field groups were situated at 34 widely spaced stations throughout the world. These outlying stations were to determine to what extent the occurrence of an atomic bomb explosion can be detected at great distance, a vitally important measure of defense. Detection methods included sensitive recording of radioactive content of the air, seismological measurements, and measurements of various radio anomalies. Choosing a target array best adapted for obtaining complete and accurate information was no small problem. Frequently, compromises in the choice of a target array had to be made by the various military units involved. No attempt was made to arrange the ships so that they would represent a fleet. This was not a test of air power against sea power. The array was not a tactical disposition. On the contrary, emphasis was on placement of vessels and equipment so that all graduations of damage would be obtained in direct relation to distance and orientation from 0 point. Such data would serve as a basis for predicting what would happen in a variety of tactical situations now and in the future. Mechanical damage was to be studied from the standpoint of ships as whole entities and of ships divided into their various parts, such as hulls, machinery, fuel tanks, magazines, and living quarters. Congress limited the number of United States combatant vessels to be used as targets to 33. In all, 88 hulls were exposed in Test Able, of which 28 were United States combatant ships. For reasons of economy, it was necessary to use ships considered inferior to those of modern design. Although in many respects, the ships used were not comparable to modern United States vessels constructed during the latter stages of World War II, these ships would provide adequate information to determine the character of damage. Since it was not known within close limits where the center of damage would be, it was necessary to disperse the ships and also the test items and instruments they carried. This, in the light of later events, proved wise indeed. Before the Able Day target array was finally selected, 19 different target arrays had been weighed and rejected. Later, more accurate and consistent figures on air blast properties became available. These supported the demand for denser grouping of the ships around the center, especially within 1,000 yards. Two British experts, Dr. W.G. Penny and Sir Geoffrey Taylor, suggested that the major combatant ships be placed in a sort of hexagonal arrangement around the point of aim. This would improve, they said, the range distribution under the random bombing dispersion expected. This suggestion was accepted and incorporated in substance. For Test Able, over a dozen moorings were used to array the central 9 ships in parallel lines. Each of these vessels was moored bow and stern and had a heading of approximately 085 degrees true. A typical mooring consisted of a buoy, a riser chain, a clump, 3 10-ton anchors, and 3 anchor chains.
The clump was a 9 or 10-ton concrete block resting on the bottom of the lagoon. It was attached to 3 or 4 anchors by 500-foot chains. The riser chain connecting the clump and the buoy was made as short as feasible to limit the swing of the vessels. The Able Day target array listed 5 battleships, including the war-damaged Nagato, once pride of the Japanese fleet. Modern German construction was represented by the cruiser Prinz Eugen, which, though trim appearing, had been bombed and repaired many times and was not completely watertight. The Nevada, the New York, the Pennsylvania, and the Arkansas were the 4 United States battleships used. While not of modern design, they possessed great resistance to battle damage. They had very heavy hull protection, torpedo protection systems, and heavy side and deck armor. There were approximately 600 watertight compartments in each of these ships. In a modern battleship of the Iowa class, there are approximately 900 such compartments and a very heavy armor deck and upper side plating of treated steel for protection against bombs and fragments. One famous ship in the array was more modern in her subdivision. This was the aircraft carrier Saratoga, originally designed as a battle cruiser and converted into one of the first Navy carriers. She had approximately 1,000 watertight compartments, 22 main bulkheads, and 2 longitudinal bulkheads through 70% of her length. Her underwater arrangement was similar to that of modern battleships and large carriers. An inner bottom above the bottom shell was fitted between the innermost torpedo bulkheads for about 80% of her length. Among the modern vessels used were the Independence, a carrier of the cruiser hull type, and several heavy-hulled submarines capable of withstanding great hydrostatic pressure when submerged. Submarines were considered among the best gauges for both tests, particularly for the underwater test. In addition to the 5 battleships, 4 cruisers, and 2 aircraft carriers, which comprised the principal ships of the Able Day target array, there were 12 destroyers of varying types, 8 submarines, 19 transport vessels, 5 modern landing ships, 30 smaller landing craft, and 3 concrete dry docks and barges. In the final plan, the intended 0 point, occupied by the flame-colored Nevada, was situated 5,400 yards from Bikini Beach. Shallow water and coral heads prevented use of a closer location. The Nevada was chosen as the central battleship because she was one of the most rugged ships available. The 4 other battleships were placed at 300, 600, 1,100, and 1,200 yards from the 0 point. The Sakawa and the Salt Lake City were placed broadside to 0 point at 600 yards. The Prinz Eugen was bow on at 1,800 yards. The Independence was spotted at 300 yards. The Saratoga was placed about 1,800 yards from 0 point, where it was anticipated she would not be damaged so greatly that she could not be used, if necessary, as the principal target ship in Test Baker. The heavy-hulled Skate was moved close in to 250 yards. 1 light-hulled and 1 heavy-hulled submarine were placed at 800 yards, a similar pair at 1,600 yards, and a third pair at 2,200 yards. An additional heavy-hulled submarine was placed at 1,500 yards. All the submarines were surfaced, so they would be exposed to the full force of the explosion. 8 of the 12 target destroyers were deployed in 2 lines on opposite sides of the 0 point, one line extending from 900 to 2,800 yards, and the other from 1,750 to 2,100 yards. 3 of the remaining destroyers were placed at 300, 500, and 750 yards, while the 4th was a full 2 miles from 0 point. The 19 attack transports were in 2 principal curved lines, one line extending from 600 to 3,200 yards, and the other from 800 to 3,700 yards. The ships of one line were almost broadside to 0 point, and the ships of the other line presented their bows to 0 point. 4 LSTs were placed in a line extending from 1,500 to 4,000 yards from 0 point, while 6 LCTs formed another group from 500 yards to 4,000 yards, stretching out toward Bikini Island. 4 LCIs were in a line beginning at 1,800 yards and extending to 4,000 yards from 0 point. 2 patrol bombers and another LCT were on the outskirts of the array. Along Bikini Beach, at approximately 200-yard intervals, were 4 LCTs, 5 LCMs, and 6 LCBPs, 1 LST, and 2 LCILs. 1,000 yards from 0 point, was a floating dry dock. A concrete oil barge was stationed at 300 yards and another at 1,200 yards from target center. Whenever possible, the ships were disposed in curved lines so that one vessel would not shield another. In the spiderweb target array for Test Able, 24 ships were located within a 1,000-yard radius from the intended 0 point. In a fleet formation at sea, it is probable that only one capital ship would be found within this radius. In a fleet anchorage, 2 to 4 ships would normally be found. In a crowded harbor with ships alongside docks or moored, a dozen or more might be in such close proximity.
Arranging the ships in the exact location specified by the operations plan was hampered by a lack of good navigational markers. Photographic surveys disclosed the errors, and ships were moved to conform strictly to the requirements. For analysis of technical data, it was necessary to determine with a fine degree of precision both the position and the orientation of each target vessel with respect to the point of detonation. Here again, major reliance had to be placed on photographs made seconds before the blast. Long focus cameras on island towers were to chronicle these minute details. One vital area was the Mach stem region, where direct pressure from the exploding bomb and pressure reflected from the water surface would be so close as to coalesce into a single cylindrical wave. Here were disposed most of the instruments to measure duration of the positive pulse, peak pressure, and shock wave velocity. Advances made during the war in television were put into practice during Operation Crossroads. Elaborate installations were made on bikini for television cameras to scan the explosions at close range and transmit the pageant of events to the scrutiny of observers and to image recording devices. Television aided, too, in aiming the drone aircraft, which were sent with split-second timing into the Able Day atomic cloud and over the cauliflower of the underwater burst. The communications and electronic plan for the operation contained a total of 203 different channels involving 348 frequencies, which ranged from 300 kilocycles to 30,000 megacycles. A constant workload fell upon electronic instruments. With the rear areas, liaison had to be maintained despite all difficulty. In the forward areas, communication and electronic problems were multiplied many-fold. Electronic science was called upon to provide systems for observing and measuring technical effects from remote locations, to operate drone planes and boats and the telemetering devices which they carried, to furnish navigational aids for aircraft, to operate various triggering devices for starting cameras and instruments, to provide television coverage of the explosions and their associated phenomena, to determine the effects of the blast clouds on electromagnetic propagation, to carry descriptions by newsmen and broadcasters to a waiting world, to deliver with utmost speed more than 400 high-quality radio photos to newspapers and magazines at home. Besides these projects, the electronics program included determination of the effects of atomic explosions upon standard electronic apparatus. Radio propagation difficulties between Kwajalein and Bikini complicated communications problems. On the Mount McKinley, flagship of the task force, as many as 6 radio, teletype, and broadcast carriers were on the air simultaneously. The proximity of transmitting and receiving antennas produced acute interference problems. Added to these troubles were sunspot and skip distance effects. Radio teletype, a new factor aboard ships and aircraft, was used extensively. For the first time, news stories were filed by radio teletype from a plane in flight. Press wordage alone, transmitted in 5 languages by radio teletype, exceeded 2.5 million words during the operation. The very high-frequency network functioned as easily as a dial telephone system, although plagued at intervals by interference and propagation troubles. Need for scrambler systems was soon established, particularly during voice discussions of highly classified topics. Communication studies were made and frequency shifts arranged. Exact tuning of transmitters alleviated but did not eliminate many interference problems. Volume of traffic was enormous. While the overall success was gratifying, completely satisfactory voice and teletype communications were never obtained on a day-to-day, 24-hour basis. Much of the communication traffic was with the Rear Echelon Organization, commanded by Rear Admiral Frank J. Lowry. During the absence of field units, the Rear Echelon had a multitude of tasks to perform in order to preserve a high degree of coordination. On Baker Day, electronic silence was strictly observed, lest stray signals interfere with the detonation of the bomb. Weather was a vital issue in both tests. Good weather, with a maximum of 3/10 cloud coverage and favorable winds, was obligatory. This placed heavy responsibilities on forecasters. 5 months before the Able Day drop, the Air Weather Service began to gather data on weather conditions in the Bikini area. They soon had many answers, particularly on upper wind structures. One type of wind, designated the east-west type, was characterized by east winds at the surface and west winds aloft above 10,000 feet. Another wind, designated the easterly type, was characterized by easterly winds up to 60,000 feet or more. It was decided that the easterly type was required for the Able Day drop, since the mushroom cloud would move westward with the wind and across open sea. Ships, aircraft, and shore-based units could thus be disposed to the windward sectors and many dangers of radioactive precipitation averted. Since required conditions would obtain only 1 day in 4, meticulous care had to be exercised in setting a suitable day. Through use of upper air wind data, diagrams were made to appraise the rate and direction of cloud movement. These data were needed to judge how far away any serious radioactive effects might be encountered. Accurate predictions, as much as 48 hours in advance, were essential because of the complexity of the task of evacuating the lagoon. New techniques for tropical forecasting were worked out. Pertinent charts, diagrams, and forecast tables were developed. Experience was gained in using radar to obtain upper wind measurements. Upper air soundings were made daily by radiosonde balloons and by high-altitude aircraft. The mobility of weather aircraft permitted rapid assembly of weather reports equal to the output of a dense network of weather stations. In addition, they provided more detailed reports of cloud conditions than would be possible from surface stations. Aerial weather reporting was augmented by ships in the area. Added was a great mass of information from the regular network of weather stations. A staff aerological unit was set up aboard the Mount McKinley, assessing weather data on a 24-hour continuous basis. Because of its importance to the success of these costly experiments, weather information was handled on the communication circuits with operational priority. Research for Crossroads demonstrated the need for an extensive network of upper air forecast stations and for complete upper air maps to high levels. Yet, so accurately were conditions predicted during the training period that operations were canceled only once because of unexpected weather. To the task force commander, safeguarding personnel was of surpassing importance. Admiral Blandy directed that every possible precaution be taken and that safety rules imposed by the medical staff be given unquestioned heed. With so many of the task force personnel exposed to dangerous conditions, the fine record of safety bears witness to the performance of the medical division. Safety advisor for the task force was Captain George M. Lyon. He was responsible for the safety plan and for the instruction of all members of the task force. Colonel Stafford L. Warren, who had been chief of the medical section of the Manhattan Engineer District, was the head of the group denoted the Radiological Safety Section. Much was known in advance about the unique hazards associated with atomic explosion. Guarding personnel against these dangers was of vast importance. The Radiological Safety Section was responsible for all measurements of radioactivity. These were required to evaluate potentialities of the explosions in causing casualties aboard target vessels, some of the most significant information sought in the experiments. These efforts meant not only prediction of intensities of all nuclear radiations, including alpha, beta, and gamma activities and neutron flux, but also the measurement of radioactivity in the air, in the water, in materials, in target and operational vessels, and near instruments and experimental animals. The group was further charged with measuring the radiation exposure of all personnel involved in the operation. In accordance with accepted safety standards, the daily limit of human exposure to gamma radiation was set at 1/10 Roentgen. Under Captain R.H. Draeger, the Naval Medical Research Section, which embraced a further complement of Army personnel and civilians, was responsible for exposing experimental animals, determining the kind and the extent of injuries, and investigating methods of diagnosis and treatment, principally of radiation illness. Hazards other than radioactivity, which damage control teams and other boarding personnel might encounter, were evaluated by the Damage Control Section. Such hazards included oil-covered decks, falling objects, distorted ladders, weakened tanks, noxious gases, flooded compartments, fires, escaping steam, electrical shocks, corrosive acids, contaminated drinking water, and secondary explosions. Not all information of benefit could be derived from instruments alone. Physiological, hematological, and pathological information was to be obtained for the study of the radiation illness, the major hazard of atomic warfare. To obtain this information at Bikini, many persons volunteered to expose themselves at vantage points of great jeopardy. Naturally, their offers were rejected. Injuries incurred by animals would provide abundant clues to effects upon men exposed to atomic explosion. Important, therefore, was the choice of animals for the experiments. Goats, pigs, and rats were selected. These species provided a range of sensitivity to ionizing radiations, and all were hardy enough to withstand tropical conditions. For specialized studies, a few mice and guinea pigs were added. Goats were chosen because their relative radiosensitivity is roughly comparable to man's. Included were 4 goats having previously established conditioned reflexes. Rats were chosen because they are less radiosensitive than man. A few guinea pigs were included for comparative purposes, since guinea pigs are more radiosensitive than man. The mice selected came from special strains, some with high predilection and some with low predilection to cancer. Seeds and grain insects were used to study the genetic effects of radiation upon plant and insect life. Besides animals, the Naval Medical Research Section was responsible for exposing a wide variety of biologic materials: seeds, hormones, vitamins, sera, bacteria, medical and dental supplies, and samples of military clothing. Resulting changes were to be correlated with observed physical data such as air pressure and radiation intensity. Collaborating in this work were the Army Chemical Corps, the Army Medical Corps, the Army Veterinary Corps, the U.S. Department of Agriculture, the U.S. Geological Survey, and the Naval Medical Research Institute. Headquarters for most of these studies was the floating laboratory, the Burleson, which was equipped for work in pathology, hematology, radiobiology, and biochemistry. Sailors with farming experience were assigned to the many tasks of animal husbandry. The animals were to be distributed on 22 target ships for the air explosion and on 4 target ships for the underwater explosion. Some were to be tethered. Some were to be placed in compartments above and below decks. Several goats were partly sheared, and anti-flash burn cream was applied to the depilated skin. Changes in the blood count are the most sensitive index to irradiation effects. Blood counts were made in the hematology laboratory of the Burleson on all animals before exposure to radiation and afterwards at frequent intervals. Some animals were to be supplied with filtered air to reduce their exposure to fission products. Instruments were placed close by the animals to record physical data for correlation with the injuries received. In this way, interpretation of the factors producing injury could be rendered. These data included intensity and duration of thermal radiation, air pressure, wind velocity, deck and bulkhead accelerations, and gamma ray and neutron intensities. Instruments brought into play were temperature recorders, ultraviolet recorders, gamma ray recorders, air pressure gauges, ionization chambers, Geiger counters, and Sony cameras for recording on film intensity and duration of the gamma ray radiation. Air purification equipment of the Army Chemical Corps was made available for testing. Collective protectors were used to filter air for certain groups of rats. Detailed records were kept of each animal. Periodic blood counts and all evidence of radiation effects were carefully recorded. The pedigrees and characteristics of many animals were already known. Particularly was this true of 120 white mice supplied by the National Cancer Institute. Simulated agents of biological warfare, sealed in aluminum cases, were provided by the Army Chemical Corps for study of mutations and other radiation effects. Effects of the bombs on soil fertility was another topic of interest, particularly to the Department of Agriculture. Caribou loam from Maine, Decatur clay loam from Georgia, and Houston black clay from Texas were exposed. Despite the excellent record in radiological safety, there were deaths from other reasons. One man was drowned. 2 deaths resulted from aircraft accidents. 1 man was accidentally electrocuted, and 1 man died of methyl alcohol poisoning. Security control throughout the operation was painstaking. Top secret details of the bomb had to be closely guarded, and extraordinary precautions were necessary because of the presence of so many observers. One of the primary security tasks involved screening of hundreds of scientists, technicians, and specialists. Detailed investigations were made of persons who would have access to highly classified equipment, laboratories, or reports. Photo review panels were set up for the release to news agencies of still and motion pictures. Photographs made in the forward areas were developed in controlled laboratories. Each photograph was subject to classification. Credentials were examined to admit authorized persons only to restricted areas. Marine guards were assigned as sentries at the bomb assembly areas at Kwajalein, and Marines also guarded vital instrumentation areas at Bikini, Amen, and NU. The Joint Chiefs of Staff, after consulting the State Department, had determined that foreign observers would be invited to witness the tests, even though the operation was secret. The positions of these observers and their access to information were controlled. Each nation, with membership in the United Nations Atomic Energy Commission, was permitted to send 2 official observers and 1 newspaperman. In all, 34 official foreign observers witnessed both tests, plus 10 representatives of the foreign press. Many of the foreign observers were outstanding scientists. Others were ordnance or technical military experts. The observers were based aboard the Blue Ridge and the Panamint. Both the Secretary of the Navy and Admiral Blandy addressed them before the tests, emphasizing that the tests were not a warlike demonstration, but serious and earnest experiments to obtain all possible information about atomic explosions in an unbiased scientific manner. Operation Crossroads focused attention of the world upon Bikini. At this distant spot were assembled many of the world's outstanding newspaper correspondents and scientific writers, still photographers, radio reporters, newsreel cameramen, and television representatives. No attempt was made to censor news copy. Thousands of news stories described the different phases of the operation in the world press. Radio photos sent from Bikini and Kwajalein established new speed records for long distance and high fidelity transmission. They were widely published. 615 commercial radio broadcasts were made from the ships of the task force, primarily from the Mount McKinley and the Appalachian. In this way, the world was made acquainted with the objectives of the tests and with their planning and execution. By the time the date was set for an all-out task force dress rehearsal, designated Queen Day, the Air Arm had achieved split-second timing and precision. Meanwhile, the spirited competition to decide which bomber crew would drop the bomb had come to an end. The privilege was won by the crew of Dave's Dream, led by Major Woodrow P. Swancutt. His bombardier was Major Harold H. Wood. Modifications to prepare Dave's Dream for the bomb were made by technicians assigned by Manhattan Engineer District. To ensure maximum precision, a Norden bomb sight was altered. The normal intersecting crosshairs were replaced by adjacent, parallel crosshairs, which allowed the bombardier to keep the aiming point image between them. The thickness of the hairs in a normal sight represents a trajectory variation of 400 feet in a drop from a 30,000-foot altitude. The bombs chosen for both the Able and Baker explosions were designed and built at the Los Alamos Laboratory. Both were of the type used at Nagasaki, the most powerful available for the experiments. For the air explosion, a detonation altitude of about 500 feet was chosen. Preparation of the bomb was directed by Rear Admiral Parsons, who commanded the bomb and instrumentation group aboard the Albemarle. The laboratory unit of this group delivered the first bomb to the crew of the plane a minimum period before takeoff. 2 weaponeers were assigned to ride the plane and arm the bomb after the aircraft was a safe distance from Kwajalein.
The Queen Day dress rehearsal was an operational success. At last, all was ready for Able Day, tentatively set by Admiral Blandy as July 1st, 1946. Throughout months of tedious preparation and preliminary tests and public discussion, tension had increased. As Able Day drew near, the eyes of the world swung toward the atoll in the Marshall Islands. The atomic bomb was topic of the day. It was on the lips of housewives, school children, and the man on the street. The cue which would set the great test organization in motion now must come from the weatherman. Aerologists watched a high-pressure area north of Midway Island, a low-pressure area in the Philippines, and a wedge of high pressure above Bikini. It was check and double check, judgment weighed against judgment, probability balanced against possibility. On June 30, the forecast came. Good bombing weather. The mission was definitely underway. According to plan, signal flags were hoisted. Promptly, evacuation of the target vessels began. Shipboard rituals of orderly departure took on new meaning. After a round of salutes to captain and quarterdeck, the colors of each ship were struck. 90 support ships must move out of the lagoon in the allotted time. Slow-moving craft were the first to leave. Larger ships lumbered after them. Before dawn on Kwajalein, the command aircraft thundered down the runway, her engines shattering the tense silence of what had seemed an endless night. As watches told 0423, it was airborne. Aboard was Brigadier General T.S. Power, the air commander who would direct the air operation from his post aloft. Fast evacuation craft dashed through the target array, embarking the last-minute sentinels. Some of these men had made final adjustments on recording instruments. Others had battened down hatches and sealed the ships. When all details were completed, yoke flags were hoisted on the halyards. Dave's dream was on the loading ramp, the bomb safely loaded, the crew ready and waiting. From Admiral Blandy at 0542 came the final go-ahead. 3 minutes later, the bomber taxied down the ramp toward takeoff position. Kwajalein had become alive. The roar of many engines contributed to the clamor. It was as if the envelope of night had given way to an envelope of sound, darkness giving way to din. Dave's dream is roaring down the runway, engines singing. She is airborne at 0555. Now, each minute counts. 8 minutes after the bomber takeoff, evacuation of the lagoon has been completed. Silence settles over Bikini Lagoon. The last ships are standing out to the open sea, heading for their stations. Among them is the Mount McKinley, nerve center of the Joint Task Force. Attention swings to the air phase of the operation. This is a tactical action involving 85 aircraft in a tight geometric formation. The air pattern contrived above the target array has as its center the vertical projection of the aiming point carried to an altitude of 30,000 feet. Around this presumed perpendicular, at given slant ranges and altitudes, and in fixed orbits, circle drones and drone control planes, photographic aircraft, radiological reconnaissance aircraft, pressure gauge dropping planes, radiometry, precipitron sampling, and oceanography aircraft, air-sea rescue units, and orientation and command aircraft. Positions in the complicated flight pattern must be accurately controlled and recorded by radar and photography. Control of air movements during and after the tests must also be guided by many other factors, particularly those of radiological safety. By 0800, General Kepner is able to report that all aircraft are airborne and that the bomber is over the target array preparing for its first dry run. Aloft, visibility is good. The dry run is successful, and at 0849, Admiral Blandy signals for the start of the bombing run. Dave's dream is at 29,000 feet. True airspeed is 299 miles per hour. The bombardier makes corrections for wind and bomb weight, and a small compensation for the inherent tendency of this type of bomb to hit short. Bomb bay doors are open. The timing signal sounds. Only seconds left to go. On the cry, bomb away, the world's fourth atomic bomb plummets earthward. As the bomb bay doors snap shut, the bomber executes her 150-degree turn to the left. The closest photographic aircraft is the F-13, which from a position 1,000 feet to the right of Dave's dream, takes motion pictures of the bombing run and photographs descent of the bomb. Instantly upon bomb release, two B-29s drop blast pressure recording instruments into the area above the target. This equipment settles into position over the array. Falling for slightly more than 48 seconds, about 500 feet above the surface of the lagoon, the bomb explodes. Unfolded are a myriad of majestic, startling, and awesome effects, a panoply that only the cameras can record in faithful detail. The most important events of atomic explosion occur during the first fraction of a second after detonation. Nuclear reaction is completed within a few millionths of a second. Then comes a brilliant flash of bluish light that overwhelms the vision of even distant observers and blanks out photographic lenses. In these heavily filtered, high-speed photographs, the flash is subdued to a glowing orb. The motion has been frozen for better discernment of the progression of events and for study of the early phenomena. This ball of fire, less than 1/100th of a second old, has a diameter of about 180 yards and is expanding at the rate of 10,000 feet per second. Before this stage is reached, gamma rays and neutrons have already escaped to produce their lethal effects. Energy equivalent to 20,000 tons of TNT now resides in this incandescent sphere as heat and pressure. Losing brilliance rapidly, it is still almost as bright as the sun. Its internal temperature, fed by nuclear energy, is reckoned in millions of degrees. Its pressure is almost a ton per square inch. At 2/100ths of a second, the ball of fire has flared to a 250-yard diameter. Less rapid is its expansion now, and a shock wave, outracing the fireball and carrying nearly half the total energy of the explosion, rushes out at 6,000 feet per second to batter the target ships. Hitting the water, the blast wave produces a reflection that rejoins the original shock, multiplying the pressures and increasing the damage. When the wave strikes the water, it produces a white circle of spray. The expansion rate of this circle provides the best method of measurement of shock wave properties. For almost a full second, excessive pressure prevails around the fireball. Then this pressure gives way to partial vacuum. Intense heat evaporates inflammable material and explosive mixtures are ignited. Flames belch against the sides of the vessels. Fires break out. Sudden rarefaction cools the surrounding atmosphere until no longer can it carry the water vapor associated with high humidity over the tropic sea. A dense cloud forms into a beautiful white hemisphere, enveloping the blazing ball of fire. At this juncture, damage from the intense heat and light radiation ceases. This supersaturation effect diminishes the number and the violence of fires as compared to atomic explosion over dry regions. High winds associated with the shock wave snuff out many of the fires which the intense heat already has created and smite ship superstructures a staggering blow. As the cloud chamber begins to dissipate, 5 seconds after detonation, a ring cloud forms, soon to be evaporated. Within this emerging fireball, there yet remains a great store of energy. Turbulent and still glowing, it shoots up with an initial velocity of 150 feet per second, carrying off all but a fraction of the deadly fission products. As incandescence disappears, the mushroom cloud develops. With powerful upthrusting surges which seem to regenerate themselves again and again, the mushroom cloud becomes a boiling mass of energy, filled with toxic gases, conflicting winds, twisting flames, and superheated air currents. The cloud assumed its characteristic shape 20 seconds after detonation. The lengthening stem and the bulbous head give it the appearance of a gigantic flower trying to span the distance between Earth and sky. Less conspicuous because of its transient nature is the froth of base cloud, soon to be sucked up into the stalk of the mushroom. At 18,000 feet, approximately 2 minutes after detonation, a thin, wraith-like cap of ice crystals has formed, quickly swallowed by the rising cloud. Within 150 seconds, the cloud has reared its majestic pillar up to 5 miles, roughly the height from which the bomb had been dropped. By 400 seconds, it has risen to 7 miles. Eventually, it reached 40,000 feet, but by this time, shearing upper winds have been whipping it to shreds. Drifting in the winds, the cloud stratified and lost its shape. Within an hour, observers at Bikini could see it no more. For many hours, reconnaissance aircraft tracked its wind-borne wandering. Later, from remote points, came reports that traces of increased radioactivity had been detected. On the way to the target array, 9 minutes before detonation, one F-6F drone developed an inoperable aileron at 28,000 feet, spiraled out of control and crashed. With this exception, the flight plan of the drone fighters was carried out with notable success. Landing at Roy, the Navy drones brought back a wide variety of scientific data and samples. Equally notable was the success of the drone bombers of the Army Air Forces. Every drone aircraft was recovered on completion of its mission and safely landed at Eniwetok. This was a remarkable record, as a high rate of loss had been expected in the remote-controlled flying operation. Instead, there was not a single abort for engine failure or other mechanical reasons. Primary mission of the drones was to gather air samples in dust-collecting bags and in air and oil filters, and to carry both television cameras and recording instruments into areas too dangerous for operation of manned aircraft. All drones also served as airborne targets to determine the effects of atomic blast upon aircraft. Its automatic cameras grinding out a photographic record, one B-17 drone was flown directly into the center of the radioactive cloud at 24,000 feet, approximately 7.5 minutes after detonation. 3 other B-17 drones were maneuvered around the outskirts of the cloud at 13,000, 18,000, and 30,000 feet. 3 drone fighters completed their transits into the cloud at 10,000, 15,000, and 20,000 feet. The drone which entered the cloud at 20,000 feet had a slight nose-up position upon entry and emerged at 26,000 feet, evidently caught in strong updrafts within the cloud. Temporarily astray, this drone was not recaptured by its control plane until 43 minutes later. It was then over Wotho. The radio compass aboard one B-17 drone proved its value when, remotely keyed, it turned the bomber toward Eniwetok while the distant control plane was attempting to overtake it. Because of its reserve fuel load, a critical factor at 30,000 feet in affecting relative speeds, the mother aircraft did not overtake the drone for 15 minutes. At Eniwetok, residual radioactivity was measured. Some of the aircraft were designated hot, their air samples indicating they had flown through areas of severe radioactivity. Airbags had been opened by AGSTOT relays when the planes were visually inside the cloud or when Geiger counters indicated they were in dense radioactive areas. The bags were closed by the radio relays 15 seconds later. Air filters allowed air to flow freely through filter paper, forming deposits of radioactive material. Oil filters also were used to collect deposit samples of the cloud. The strongest samples of radioactivity were obtained from aircraft which had flown through the cloud at higher altitudes. All drones carried flight analyzers which recorded normal accelerations, air speeds, pressures, and altitudes as functions of time. Because they were distant from the epicenter at detonation, the drones did not experience any marked acceleration from the shock wave. Air currents did produce mild accelerations of the drones at the threshold of the cloud pillar and within it. As far as engine performance is concerned, it was established that aircraft can operate close to atomic explosion. The drones carried a great variety of electronic equipment for testing. Results of electronic investigations were generally negative. So little electronic or mechanical interference or malfunction was recorded that it may be strongly assumed that radio-controlled drones or electronically controlled rocket missiles can be used successfully in areas close to an atomic explosion. Radioactivity had little effect on transmissions. A strange effect was produced upon the iconoscope of the television camera in the nose of the B-17 drone which entered the center of the cloud. The light intensity of the detonation was so great that a miniature image of the early blast was burned permanently on the screen. The iconoscope is being preserved at Wright Field. No radar reflections were obtained from the blast cloud in Test Able. Attenuation of signals which passed through the cloud was observed, the phenomena lasting as long as 7 seconds at the higher radar frequencies. A few minutes after detonation, the BGOR, jointly controlling the drone boats with the aid of aircraft, approached the lagoon for visual control. At the same time, 4 TBM planes were launched by the Sidor with conning officers and radiological safety monitors aboard. 44 minutes after detonation, the first drone boat, an LCVP, its stern trailing a cloud of smoke to identify it to the control planes, started toward the target array to collect water samples. Another followed a short interval later. Within 4 hours of detonation, these radio-controlled boats had collected a number of water samples which were immediately flown to Kwajalein for analysis. Other aircraft were performing important functions. A PBM equipped with special radiometry instruments to photograph and measure the heat radiation of the blast orbited the target array at 9,500 feet and 15 miles slant range. This equipment produced particularly valuable scientific data. Radiological reconnaissance aircraft and photographic aircraft continued their flights for a long period after detonation, being replaced periodically by relief aircraft. These crews acquired a steady flow of the data necessary to maintain an uninterrupted record. 3 seaplanes carried equipment for photographing and measuring water waves resulting from the burst. The crew of one of these planes also actuated by radio the synchronized tower cameras on the islands. Close inspection of the damage wrought by the Able Day bomb awaited completion of safety precautions. Through binoculars, the distant watchers had seen a number of fires break out. They had strained to identify the ships involved. As the blast wave passed over the ships, observers had noted a black cloud above each vessel. Scientists believed that these clouds consisted of soot and dirt shaken loose by the blast and forced out of the stacks and boilers of the ships. Salvage units awaited the signal for re-entrance to the lagoon. These units were equipped with safety helmets, rescue breathing apparatus, mine appliances, and other instruments designed to detect and measure noxious and explosive gases. 5 hours after detonation, after careful radiological survey by the safety groups, the word came from Admiral Blandy, re-enter. As units steamed into the lagoon, full import of the tremendous effect of the atomic bomb became immediately apparent. Spread over the oil-splotched lagoon, observers saw a vast array of smoking, soot-smudged vessels as if the remnants of a great naval conflict.